Okay, welcome back. We're going to finish up our impulse and momentum notes by talking about conservation of momentum. And I know that we did this last year, and this is actually usually one of the better units for you guys. Not be Usually because this ends up becoming so mathematical, and you guys by this point I think are used to the math, at least in Regents. In class, I am going to try to make a little bit more of an emphasis on the conceptual ideas behind conservation of momentum, but that doesn't mean we won't do mathematical problems as well. Okay, so conservation of momentum, one of the first, well, I guess earlier this year we talked about conservation of energy. This is another conservation law. And we know that in conservation laws, we use them because in the sequence of events of something happening, if a conservation law is relevant, then some quantity does not change. And that is usually subject to some sort of condition. And there happens, so we already talked about the law of conservation of energy. We're now going to talk about the law of conservation of momentum. If I were to put it in words, conservation of momentum refers to this idea. Total momentum before some event is equal to the total momentum after an event if the net force is equal to 0 newtons for the system in question. And that's very important that we talk about this idea of a system. Okay, it is actually really important, even though it seems like something that's very simple, just like making an axis or labeling your free body diagram. Writing out the system or explicitly defining your system is actually very important, because momentum is only conserved if the net force on your system is 0. So take, for example, an object that is at rest and then another object collides into it and causes it to start moving. If your system is only the object that was initially at rest, then you can't say that the net force during that interaction is 0. And therefore you would use the impulse formula. The impulse is equal to the net force multiplied by the time, which is equal to the mass times the change in velocity, to figure out what happens to that object. On the other hand, if we were instead to say our system comprises both of those objects, those two objects exerting forces between them, those are forces that are internal to our system. Okay? Any internal forces in a system do not count towards the net external force, the external net force on our system. So we would say, if we're looking at both of those cars as our system, that momentum is conserved if we're looking at the two of them. If we're just looking at one of the cars, we would say, no, momentum is not conserved for just this one car, but that's because there was a net force on it. Either way, we can still analyze the system in slightly different ways, but we can still end up with the same answer. Okay, so defining the system is very important. We'll practice that as we go. Symbolically, in equation form, this is very simple. It's a deceptively simple equation. Momentum initial equals momentum final. But this equation can be expanded out as needed to fit the situation. So you're building out your own equations with this. Why do we use this? Why do we use conservation of momentum? We really like it for interactions or situations where objects crash or explode or stick together or bounce, etc. Where objects crash, explode, bounce, stick together, etc. Okay? And why do we care about them here? Well, if you think about it, if you have anything more complex than even just like simple spheres or blocks colliding, those collisions get very complicated very fast. you've got different parts hitting each other. The forces in these interactions are very complex. So what conservation of momentum, I'm going to abbreviate CONS of MOM, what it allows us to do, allows us to make predictions about what will happen or what has happened if the initial and final conditions are known. In other words, we can ignore the details of the actual interaction itself, as in the exact forces that are that are being exerted. We can just look at what happened before, what happened after. It's kind of like a nice little shortcut. Okay, so let's get to some steps for solving problems involving conservation of momentum. And just like I did last year, I think I'm going to try and do a little bit of both. I'll show you the steps, and then we'll apply them to a certain situation. So the first step in any conservation of momentum problem is for you to make sure that F net is actually equal to 0 newtons for your choice of system. So I guess really what we need to do is we need to pick our system first. Okay, so we need to make sure that F net equals 0 newtons for your choice of system. So in example number 1, a cart of mass 4 kilograms initially moving at 3 meters per second east strikes a stationary cart of mass 6 kilograms. If the carts stick together after the collision, what is their velocity and was energy conserved? So what I'm going to look at here is I could pick a system in which it's just one of the carts or the other, but the carts end up together at the end. So it kind of makes sense for me here and in a lot of these other problems to treat both carts as the system I'm looking at. Those carts, they're moving probably in the horizontal direction. I know it doesn't say it, but let's assume. And they do interact with each other. They do put forces on each other, but neither of those contributes to the external net force on the system, since they're internal forces. They arise from objects that are inside our system. It's an interaction within our system. So as long as there's no friction, it doesn't say anything about there being friction, we can assume that the net force on this system is 0. That doesn't mean there's no forces on the system. There is force of gravity, obviously. There is probably a normal force from the surface they're on. But there are no net external forces in the x direction. Again, the forces between those cars are internal. So the net force should be 0 for our 2-cart system. That's good. We move on to step 2. And again, if it were to say that, hey, there is friction acting on these carts, that doesn't mean that you can't solve the problem. If there's a net force on the system, that doesn't mean you can't solve it. That just means you can't really use conservation of momentum. You do have to use the impulse formula and what we talked about in the last few videos. Step 2, once we've verified that we can use conservation of momentum, is to write out the equation. Write conservation of momentum equation. And there's a bunch of things that you need to consider when doing this. Me personally, I like to build out my conservation of momentum equation. So I'll start with something simple, like P naught equals P. That's a correct equation. You're showing whoever's grading your paper that you know that momentum is conserved. From there, I like to consider a couple different things. How many objects are there before and after? Now this might sound like kind of a stupid question because you're like, well, there's 2 carts, so obviously there's 2 before and 2 after. But it says that the 2 carts stick together after the collision, so we can really treat that as if they're now just one object. So allowing for both objects to have momentum beforehand and the object afterwards to have momentum as well, I might have 2 terms on my left-hand side initially, 1 term on my right-hand side. We might also want to consider which direction is positive. Is there directions in this problem? It says that the cart of mass 4 kilograms initially moving at 3 meters per second east And it doesn't say any other direction, so we might as well make east positive. So any reference to east, we're going to know is going to be a positive number. And likewise, any positive number that comes out as a result means to the east. Last thing I want to consider, what variables are you given? This will kind of inform how far down the rabbit hole of expanding this equation you have to go until you have an equation you can plug into. Which variables are you given? A lot of times I see people go all the way down and get everything in terms of masses and velocities, but then realize that, hey, I was only given the magnitudes of the momenta, and so therefore they did too much work. It looks like here, though, we're given masses and velocities. So what I'm going to do is now I'm going to write out my equation, and I'm going to say, okay, so here's my first object, m1 v1 naught. So that's the mass of the first cart and the initial speed of the initial velocity of the first cart, plus m2 v2 naught, that's for the second cart initially, equals my two objects come together. I'm going to combine their masses because once they're locked together, the mass of of the one object that they make up is just the sum of the two masses times their velocity. Okay, and then step 3, the most basic one, is simply solve. And I will make a little note down here. Last year you didn't really have to do this, but this year we will mix in occasionally some energy questions. So occasionally you will have to use both conservation of momentum and conservation of energy to solve, or at least the question will be about both of those topics. So we know that we have a cart of mass 4 kilograms. Let's make that m1. That would make more sense. So 4 kilograms times 3 meters per second east. We said that's positive, so no reason to put a negative sign on there. Strikes a stationary cart. Stationary means not moving, so no initial velocity. I'm just going to cross that off and write 0. Once I've got it in the equation, I'm just going to cross it off and write 0. The cart's locked together. So that's a mass of 4 kilograms plus 6 kilograms. And we're looking for the final speed. 4 times 3 is 12. 4 plus 6 is 10. I divide both sides by 10. And I get 1.2 meters per second. And again, that's positive, so I know that we're talking about east. Okay. Now, there is another question. That's the final velocity. Was energy conserved? How could I test this? I just need to see if the initial energy is equal to the final energy. What types of energy are we talking about here? There's no mention of springs. There's no mention of thermal energy. There's no mention of any varying heights. We're strictly talking about kinetic energies. So I want to know if the initial kinetic energy is equal to the final kinetic energy, which means what I want to know is, since the kinetic energy formula is 1/2 mv squared, 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared equals 1/2 the combined mass m1 plus m2 v squared. Okay, there's some simplifications I can make here, okay? And I'm just going to put a question mark here because we don't know that these are equal to each other. We're just looking to see if that is the case. All right, so let's see here. There are some simplifications I can make. I know this is an initially stationary cart for m2, so this whole term is going to go to 0, just like it did over here. What I'm left with is 1/2 m1 v1 naught squared equals 1/2 m1 plus m2 v squared. You'll notice I have a 1/2 on both sides. I'm going to cross those off, because if I divide both sides by 1/2, they'll go away. Now I can plug in. m1 is 4 kilograms, v1 naught is 3 meters per second squared. That's equal to 4 kilograms plus 6 kilograms times 1.2 meters per second squared. 4 times 3 is 12, times another 3 is 36. And again, that's not in joules. This isn't in energy because I haven't calculated an energy. I've done mv squared. That's not anything. If I put a 1/2 in front of it, then I could use units of energy. But right now, I can't. Let's see. 4 plus 6 is 10 times 1.2 times 1.2. I end up with 14.4 on this side. These are clearly not the same, and so we have energy is not conserved. So why not? This wasn't an elastic collision. We didn't have energy be conserved. In an elastic collision, the objects would bounce off each other. That doesn't mean every collision where objects bounce is perfectly elastic and all the energy is conserved, but we know for a fact that when two objects hit and stay stuck together, that is a totally or perfectly inelastic collision. Okay? It is a perfectly inelastic collision. It actually causes the maximum amount of energy loss. And energy is never conserved if objects stick together. Where does the energy go? Well, it becomes sound energy because the objects stick together. There's some residual heat energy, that gets some of the kinetic energy transfers to heat energy. The point is that all the kinetic energy from the beginning is not there at the end. Okay? When we come back, we'll do a few more examples of conservation of momentum.